From Chicago, welcome to 3Degrees Discussions. I'm your host, Mike Vasquez. This is a podcast devoted to the stories behind the innovators, entrepreneurs, and leaders in the 3D printing industry.
Why additive manufacturing is so important for rocket propulsion and space applications is that the quantities of parts that we typically build are low enough that we can invest a lot of time and engineering into making them extremely efficient and well applied to their particular niche application. And what that then does is it drives up the value of individual parts.
That was Tyler Lebrun. Tyler is a principal member of technical staff and additive manufacturing lead at Sandia National Labs, where he is focused on all aspects of AM technology and research. He has an extensive background in aerospace, having spent time at Aerojet Rocketdyne, as well as Blue Origin. Tyler is also heavily involved in the development of standards for the 3D printing industry, and shares some of the behind-the-scenes work that goes on to help industrialize the technology. Before we get started, head over to www.3degreescompany.com and subscribe to the podcast. Remember, you can listen to the show anywhere you download your podcast, including Spotify, Apple, Amazon, or Stitcher. Thank you so much for joining the show today. I've been a big fan of your Manuscript Mondays, and luckily we're recording on a Monday, so it seems fit. I like to start all of these conversations with a little bit of context of the guest and give people some perspective of where you came from, kind of your path to additive manufacturing. So let's start at the earliest stage, kind of where you're born, kind of what got you on the path to additive, what was kind of early days in school and that like for you.
Sure. Thank you for having me on. It's great to be back on the show. To go back all the way to the beginning, I guess. So I did my undergraduate at UC Berkeley, and at the time, additive manufacturing was looked to as a rapid prototyping tool. And my first job out of undergrad was working for Boeing Commercial up in Everett, Washington. And so they had a display case inside some of the buildings where they had plastic parts that were prominently on display, showing just the prototyping capability for some of their products, mostly on the interior side of the aircraft, so things that the customer would be able to touch and see. But it wasn't really manufacturing just quite yet, and that would have been way back in 2006, 2007 timeframe. I went to work for, at the time, Pratt & Whitney Rocketdyne. It's now Aerojet Rocketdyne, but they started to toe dip into additive manufacturing with their partner, NASA, down at Marshall Space Flight Center, specifically on the very first piece of hardware that I was a responsible engineer. And that would have been the J2X engine program, the gas generator discharge duct. It sounds very exciting, but all that it was is just basically a bent tube that connected the gas generator with the inlet to the fuel turbo pump on the turbine. And it served not only as the discharge by its name, but it also was a combustion chamber in and of itself. And we had a lot of difficulty having our analysis loop close for the design, considering the thermal gradients from a cryogenic gas generator all the way down to the inlet of the turbine, where we're seeing like 1100 degrees Fahrenheit. And so the bent tube design, we had a parallel path that our materials engineer decided to pursue, which was at the time direct to metal laser sintering using an EOS platform, partnered with then Morris Technologies. And so I got to see firsthand us build these prototype hardware, fully inspect them, put them on a test stand down at Marshall, hot fire test them, and then NASA did a full destructive test of those particular articles to understand how the material behaves. People were very concerned, of course, at the time, of porosity and defects and whether or not the material was just as good as, say, the rot properties that we were looking for. And it passed with flying colors. And so that was my first introduction to AM in general. But we began to explore other applications at Rocketdyne. Even at the time, we were considering resurrecting the F1 engine, which is the main booster that went into the Saturn V. So if you think way back to the Apollo program, the very large engines at the bottom of that rocket, they were considering at the time of bringing that back as a product. And so rather than some of the handcrafted production that they had done in the past to make some of those parts, they actually were considering to leverage AM for some of the more complicated geometries. And so I got to participate in some of the material investigation work early on some of the AM prototypes we were building and some of the very limited alloy selections that we had at the time. Fast forward a few years later, after I finished my PhD in Japan, I worked for Blue Origin, helping to stand up their process for AM across a number of alloys, as well as some of the capital investment and some of the other process decisions that we needed to make in order to streamline the introduction of AM into some of the engine design and development workflows. So I worked there for a few years, and then coming out of that, I worked for a startup in the Bay Area called Uniformity Labs, which is a powder feedstock production company. And so their main pitch was that they could improve the productivity of machine platforms by leveraging some very clever IP in the powder space, as well as how to operate creative scan strategies. And that allowed us to see multipliers in terms of print speeds. And so from there, I went to work for the National Labs, specifically Sandia National Laboratories. And so I still stay in the Bay Area. I work in Livermore, California currently, and I've been there for about a year and a half now. But we're the only national lab that's plural. Our mothership, as we call it, is down in Albuquerque, where most of the staff is located. But I'm one of the lucky few here in California. So now my current role as the additive manufacturing lead, I manage a diverse portfolio of research projects that help to further the adoption of additive manufacturing and push kind of that research envelope a bit in specific application spaces that we care about. But everything under the sun, from ceramics to plastics to metal to DED to powder-based technologies, you name it, we've got our hands on it. So I've got kind of a really good bird's eye view of what's going on and trying to leverage industry and all the relationships I built over my career here in the labs.
Awesome. A lot to unpack in a extensive career. So I'm going to start kind of maybe a little bit further back on some of that. So as you were kind of starting your career, looking at some of these first parts that were being made and the process of qualifying those, like what was kind of the company's perspective when you're working with NASA on like, why is this a viable, or why should we even be exploring this type of technology? And then kind of from your perspective, like what did you see in the technology that got you hooked or got you interested in saying, hey, there might be more to uncover here, unpacked, and I want to work on that?
Absolutely. In terms of why AM, and we see it even still today, significantly today, but why additive manufacturing is so important for rocket propulsion and space applications is that the quantities of parts that we typically build are low enough that we can invest a lot of time and engineering into making them extremely efficient and well applied to their particular niche application. And what that then does is it drives up the value of individual parts, because the overall assembly is fairly complex. And it's typically, we're squeezing out our structural margins, we're squeezing out our performance margins on the hardware. And so we basically are leveraging things that are difficult to produce via conventional manufacturing. And in the case of some of the older techniques of creating combustion chambers and other injector components and other things that are difficult to manufacture, AM provides a shortcut in terms of reducing overall complexity by allowing us to basically consolidate assemblies into monolithic parts, which then drives up or allows the designer to have access to creating more complicated, more efficient designs. So rocket propulsion is really well suited because AM has kind of a throughput problem. We can't make thousands upon thousands of parts compete with some of the more conventional techniques. But when you're only making dozens of parts, you can really leverage the technology in that particular space well. And so when my career started, I was not in materials. I was more in the design space. I worked in the engine systems design group on the J2X program. And I saw additive at the time from the perspective of a designer, that it allowed me to have access to design regions that were otherwise unavailable to me because I had limitations on design for manufacturing. So I had to find ways to use the material choices and the assembly technologies that were available at the time to create more or less conventional designs. So AM really unlocked a lot of opportunity in what we could do for efficiencies in terms of packaging, in terms of weight, all sorts of things across the spectrum that are just not available from conventional methods. And so that's what really opened my eyes. And I was like, wow, this is really exciting. I can do a lot of really cool stuff. And then I had kind of a growing interest in the materials, just independent of additive manufacturing. And I was like, how can I leverage the two? And so that's the direction I ended up taking my career through the PhD, was more of a materials focus. So having both the design background, but then now interest in the material side, that combination served me very well in the additive manufacturing space.
Yeah, it's one of those things where you can get a job anywhere in the world with that sort of background in additive.
That's right.
So on that front, I mean, digging into kind of starting on the design side, it's always been my perspective that understanding how the process works from end to end is critical for designing additive parts, right? Like you may be in front of a CAD model or a CAD station using Anthropology or whatever software tool you're using, but like seeing the physical part be made, how it's cut off, the post-processing, the heat treatment, any other surface things you're doing to it is critical to give context to it. So how did that kind of evolve? Were you running machines? Were you kind of participating in kind of the day-to-day activity of building, or kind of where did the, like, even on the material side, where did that start as well?
Sure. So the exposure at Rocketdyne was fairly limited in terms of we weren't making parts ad nauseum. We weren't throwing everything we could at the printer to figure out what we could and couldn't do, kind of stress test the technology, partly because we didn't own a printer. We were doing everything with an outside supplier. So our choices in terms of what we were pursuing were fairly limited at the time. But if you fast forward up to my time at Blue Origin, at that time, they had really kind of doubled down on the technology. And so they had invested quite significantly in terms of the number of machines, the diversity of different types of platforms. And so from there, not only was the materials and process team responsible for helping to stand up, in many respects, the qualification of the materials themselves as a consequence of the process, but serving kind of as the bridge between the design engineers and the manufacturing engineers to say, this is what we can do with this technology. This is at the very early stages of like design for additive manufacturing, DFAM. And so we were basically kind of learning as we went what did and didn't work, creating that kind of documentation to provide feedback to designers to understand what these are the limitations of what you can and can't do. And then while simultaneously trying to characterize the materials to give enough information to the design teams to say, well, this is your performance envelope you can work in for this alloy. And just as an example, if you're concerned about, say, thermal conductivity for whatever your main combustion chamber looks like or your injector elements look like, then this is what we've done to characterize the additive material that's coming out of the printers. So you can then know, this is my wall thickness, this is what my design margin looks like. And so that full cycle was incredibly important to being able to realize product that we knew we could put on a test stand with a decent set of expectations that we would be successful, minimize the amount of unknown unknowns that were out there. But yeah, so that, I mean, we had our hands on everything at that early stage in the company when we were really adopting additive. As it became more and more mature, the workflow really started to settle and people's roles and responsibilities became a little more narrowly tailored. But when I left to come down to the Bay Area, there was still a lot of early alloy development process that was going on, helping to do that full characterization and give the design teams enough information to design their hardware. And then we were, again, still learning how to kind of tweak the DFAM space as best as we could for the applications we cared about.
And when you say the technology, the processes matured, are you specific to like, hey, the machines got better and we're confident that this will build? Or is it like, hey, we know kind of where our upper and lower bounds of what we can and can't build?
I would argue it's everything.
Okay.
It's kind of a cop-out answer. the machines did improve. So we did, I mean, just as a kind of a very narrow example, like on the EOS platforms, we did get to see the transition on the gas inlet design as it matured across the iterations. So that change impacted the gas flow behavior over the powder bed. We encountered some of the early questions about overlap regions on the EOS M400-4. So those kinds of things that we would then have to wrestle with in terms of what is the amount of uncertainty, how can we live with that? Those types of things did mature with time in terms of our understanding and impact to the parts and their reliability and the margins that we could apply to them. But we also looked to how could we design for the process in terms of the material space on the alloy development side? Can we make changes that are uniquely appropriate for our products, operating in cryogenic temperatures and also extremely high temperature applications? Are there ways we can really kind of dig into that? And so a lot of the colleagues I had spent a lot of time working on alloy development in the chemistry space to try and find the right suite of materials that would work well. And so that matured. But I think a lot of it is just kind of rolling up your sleeves and getting your hands dirty, is just the experience of finding out what does and doesn't work. And that's where sometimes some of the organizations I've worked with in the past have struggled because it's the lack of time with the equipment to understand and build up that kind of fundamental understanding is to be successful in the technology.
And so your current role, you're at Sandia National Labs. Do you want to just kind of give a 30-second overview of like what is a national lab for someone who might not be familiar with that?
Sure. Sandia National Laboratories is a FFRDC, or a federally funded research and development center. We support a variety of Department of Energy programs, but we do a lot of fundamental research. We touch everything across the spectrum, things like national security to energy security to fundamental material research, you name it, we've probably got somebody working on it. We're a very large organization. I think we're, if I remember correctly, like 14,000 people in Albuquerque, and then a fraction of that here in Livermore, California. But we've got a lot of good relationships with other national laboratories that are in our same space. So Los Alamos National Lab, Lawrence Livermore National Lab, Oak Ridge National Lab, they're all good colleagues and partners in the work we do. But we have, my specific space is focused on additive manufacturing, but a lot of kind of the fundamental research and process development side is where I'm primarily focused on.
So with that, maybe two questions. Kind of, you want to take us through kind of a typical day of kind of what you do and kind of the work you're doing, and then I think one of the other questions that I'm always curious with, especially with fundamental research, is how do you judge that you're going down a right path, right? Because you're planting seeds, right, all over the place, and timescales may be different, and how do you balance the need to show progress versus the potential of a given idea?
Sure. One of the things that I think that I bring a lot of value to here at the labs is my career isn't limited to just my time at Sandia. So I've spent over a decade working in aerospace, and that time has given me exposure to a lot of processes and ways of thinking about manufacturing workflows. And so that appreciation influences where I think the research dollars ought to be spent, because at the end of the day, we're still talking about a manufacturing technology. And so by providing context and providing sufficient direction on how the research at the end of the day supports that manufacturing application, that's where I am providing the most value for the work we do. And so oftentimes, people in academic roles can sometimes really go down a rabbit hole and find a lot of it interesting fundamental science. But if it doesn't circle back to ultimately how does this technology apply to some sort of product or some sort of piece of hardware or some workflow that we want to try and stand up and then push out to some other partner, then the utility of that work isn't as strong as maybe something else more focused on that manufacturing end use application. And so that's where my day-to-day typically is spent providing more of a consulting type role, surprisingly. All the experience in terms of how we qualified hardware at Blue, how we qualified hardware at Rocketdyne, just in general, from my exposure to colleagues at other aerospace companies, how they qualify hardware. So that type of experience is what's helping to drive the direction for the work that we do, or the work that I'm responsible for at Sandia National Labs. But day to day, oh gosh, every day is different. I know that's kind of a cop out, but there is no set schedule other than I'm usually in meetings almost all day, every day, helping to basically provide guidance to product teams. They're like, well, how do we qualify this on this particular process with this material? Do we really care about performing a bunch of mechanical tests if we don't have any requirements for it? I'm like, well, no. So it's providing that kind of ground truth appreciation as to what does it really take to get stuff over the finish line. That's kind of where I am spending most of my time with the product teams, the researchers. I'm doing a lot of work on writing internal documents for procurement and standardization of how we go about our day-to-day on additive, which then bleeds over into the volunteer work for outside industry. But yeah, it's more of like the consulting type posture is kind of how my day-to-day looks like, everything that comes with it.
And so on that front, does it, so you're doing fundamental research, you have a number of machines throughout the lab, with the lab ecosystem.
Sure.
Then do you partner with manufacturers to actually manufacture something, or are you actually manufacturing parts, components, things on site for use in the government?
We do a little bit of both. The machines on site are commonly used for prototyping and the research focus, so more on the material side and then the process side, but the end application of producing parts in a quote production environment is not something that the lab necessarily does. And so we have partners that we do work with. The end goal being that whatever material and process and equipment combination that we help to establish is what we're going to pass on to our production partner, and basically streamline all that effort so that they don't have to go figure it out, or we have to then pay them to figure it out. We do it ourselves. We work very closely with a number of partners within the Department of Energy, as well as outside suppliers for producing one-off parts, or even downstream into production for some of the programs that we support. But yeah, we don't do much of the production yet, as much as maybe on some of the other types of hardware that we have the best internal understanding and appreciation for the material science we might end up doing. But for now, everything is being pushed out.
And so you briefly mentioned it, but I want to dig into it a little bit more of all your volunteer efforts in standardization and creating standards. You're hugely involved in that community. So how did that get started? Kind of maybe specifics on kind of
Sure.
what you're working on there.
I smile because that's probably one of my favorite things I do as part of my job. Even though it's volunteering outside of the labs, it does have a huge impact internally. But I was introduced to the standards community when I was working for Blue Origin by a gentleman by the name of Daniel Reeves, a good colleague and friend of mine who is very active on the SAE Aerospace Material Specification Metals Committee for additive manufacturing. And he and another colleague of mine at the time, Hallie Deutschman, both of them worked on the SAE committee for standards. And so I really wanted to get involved somehow. And it wasn't until I moved on to Uniformity Labs that I was able to, and that partly is because we couldn't have too many participants from the same organization on the committee to sway how ballots go one way or the other. So it wasn't until I moved on to the next job that I really kind of jumped headfirst into that. And so seeing as how some of the standards that were being written might impact the application of what we were developing at Uniformity Labs, that really provided the business justification for me to be actively doing that as part of my day-to-day job. But then even now, working for Sandia National Labs, that work is incredibly important because it helps to provide context for what almost feels like vetting of a process and material, and how we can then apply it internally. So if a bunch of other people have said this is the right way to do it because it's been reviewed as part of a formal ballot process, because people see that this is the way that we should standardize, it provides sufficient context in terms of its application and uptake internally to the lab complex. So it kind of helps fast track the adoption of technology when we do have standards. And we see that across the industry in general, that with standardization, that helps to streamline the adoption of the technology. But my work there is across the spectrum, from binder jetting to laser powder bed fusion. Most of the time I've spent work developing standards on the powder side, since that's where most of my experience has been. But it's not limited to that. We just recently released in the last couple months AMS 7031, which was the first standard to cover the preparation of used powder for reuse. So colloquially, what we refer to as recycling. But that's meant for the batch processing machine. So when you think of the platforms that you have to dump powder in and take it all out after the completion of every build, those types of pieces of equipment this document was written for. Next step is to write the same thing, but for like closed loop machines. So those that are fully internalized, sieving, and then also returning basically prepared powder back into the hopper for the next continued build or for the next build. That's the next set of equipment that we're planning to work on in the not too distant future, because it looks like most of the industry is moving that way.
So what's yours, like, you want to walk us through kind of how a standard is made and kind of like what are you doing to help facilitate that process?
Sure. It's an exercise in herding cats is how it usually is described. And the way it usually works, it doesn't matter which standards development organization or SDO that does the work, the process is pretty much the same. Usually a project is proposed, and that project will have a sponsor of some kind. In the SAE world, we refer to them as a document sponsor, but we have typically a primary technical point of contact that helps to shepherd the entire document through its development and its balloting process. But basically, that project is proposed to the committee. It gets kind of the thumbs up or green light from the steering committee that this is indeed what the industry is looking for. There are typically expectations on usage for that document before it's released. So there typically has to be, in the case of SAE, for simplicity, if we're talking about a powder specification, there has to be at least one producer and 2 users. The same is true for the end use material. There has to be at least enough traction already out there to justify the time and energy spent and the release of that document. So we have to show that there's sufficient reason to do the work. But once we've gotten the green light, it typically comes down to the document sponsor to write that rough draft, and if necessary, work with kind of a working group on an as-needed basis. And for that last document I mentioned, we spent about 2 years meeting every week to discuss the contents of the draft and keep just massaging it over and over and over again. And that working group contained participants from industry in the powder production space, the users of the technology. We had representation from academia. We had representation from federal regulatory bodies. So the FAA was present. So we had everybody under the sun working on this document with me over the span of 2 years, until finally it's at a point where we think, okay, we've gotten it good enough to push it out for its first ballot to get formalized comments back from people. And once we get those comments back, we're able to then basically start to fine tune the language that's in the document, make sure that we're not saying something unintentionally or allowing some loophole to be present. But after, I think that document went through at least 3 different ballot cycles before it finally started to show up in what's called a limited scope ballot. So we had enough of the document with a minimum number of technical negative comments responding back that we could start to say, this portion of the document's done. We're only going to focus on this narrow section here. And so it went through a couple limited scope ballots until finally, I think we got enough buy-in from the committee at large after meeting the minimum vote requirements by the members of the committee that it finally was complete. And then it's got to go through a whole different ballot cycle with the Aerospace Council at SAE. And that's kind of a last check by people that are not part of the Aerospace AM Materials Committee. So they'll get to look at it once, and then if nobody has any issues with it and it gets approved, it then probably sits kind of in a document prep cycle for about a month or 2 by SAE or whoever the SDO is, and then it shows up available for purchase by the industry at large. So quite an involved process, but some of these documents take a lot of work, and we like to put out good documents, so they require the attention that they receive. So they're not something we do just overnight, but I'm expecting this next one to take probably just as long as that last one just because of how important it is. And so there's a lot of people kind of saying, hey, I want to help. I want to help. Like, that's a lot of cooks in the kitchen, but we'll get it done. We'll get it done.
Yeah, and I mean, kudos to you for the volunteer hours and days and weeks, that years that it takes to get something over the line, because you're inspecting every single word, every single concept, and things are constantly changing, right? And the personalities and egos that you have to manage.
Oh,
it's
yes.
Probably not an easy chore.
That's right. The other thing I probably is worth mentioning is that as the industry begins to develop these standards, the intersecting web of the documents becomes more and more complicated. And so we try to anticipate early on how the documents work together to create basically an interconnected set of documentation to help standardize the entire workflow. And that's really important to appreciate when we talk about things like when we call out a powder spec, that powder spec cites the powder production process control spec. And that powder spec also calls out our powder sizing document. And so there's all these interrelated reference documents. And the same is true for the one we just released, that we point back out to a bunch of other documents that we have to make sure that we're not in conflict with, that we are able to properly cite and leverage, and that suddenly the way we're using it doesn't get revised out or something changes. And so there's a lot of, you have to think multiple moves ahead to make sure that the work you're doing is somewhat self-supporting in the ecosystem you're in, but that you're kind of anticipating the needs of the industry as well. So there's just this back and forth juggle that happens with coming up with the right language on these documents.
For sure. And so with that, I mean, you're kind of diving into kind of the literature all the time. Where was the idea for Manuscript Monday? Where did that come from?
Manuscript Monday was me trying to find a way to carve out my own little small niche on LinkedIn. There were a lot of people that were doing things actively, and it just seemed like there was a gap in a regular appearance of anything discussed in the academic space. People would commonly say, hey, I published a paper, come check it out. But that's kind of where it stopped. And so when we didn't have anyone actively just taking a paper, discussing what the implications of that research were, how does it apply, why is it important, and then pointing back out, and then recognizing the authors as well. I think for a lot of, and this, I mean, I could empathize with myself here in the past, that having recognition as a student is incredibly important to getting kind of your name out there. So giving kudos to the authors is really important part of the Manuscript Monday process, is just to make sure these people did a lot of really good work, check them out, and then here's just kind of a brief synopsis of what we think is important in the document and why it's important for either some process, or here are some open-ended questions that are worth discussing about what this paper basically opens up. So that is kind of a different way that I was able to give back, is just to have that kind of open dialogue and highlight the work of really good researchers that are out there.
Yeah, it's awesome. I mean, for me, like, I don't get a chance to keep as much up to date on all the academic papers as I once was able to, but like seeing like something new come out and like, hey, if it looks interesting, I get to have like that instant, like someone else has vetted it for me. Is like, oh, like this seems like an issues paper. I'll check it out. So I really like it. It helps me kind of streamline kind of what I'm looking at and what is coming down the pike on new research.
Yeah, it's important. Oftentimes there is work we do in the labs that, I mean, we're constantly having to keep our finger on the pulse of what's being done in research, because that informs whether or not we're either duplicating effort or is there something to learn from others' work. But there are a lot of tools that I use to try and keep on top of that stuff. Like even like Google Scholar alerts, just keep me at the forefront of what's being released on a daily basis. And then I'm like, okay, I have to write. It's Sunday night. I got to write Manuscript Monday and get ready for that this week. And I'm not always on top of it either. There are some Mondays that I do miss. And I just hope nobody notices.
Yeah, I don't think people are. They won't hold your feet to the fire. I think all the work that you've done is awesome there. So I guess one last question. Kind of what's what are you excited about for the rest of the year, for the rest of 2022? I mean, you're going on this long hike, so personally, I'm sure that's exciting. But kind of from the additive world, what are some trends that you're seeing, or some non-top secret stuff that you're seeing on the work side that is going to continue to impact the industry?
I would argue that the what's really exciting that I'm looking forward to is that even though COVID really hasn't gone away, people's posture, people are learning how to live with COVID to the best that they can. And what that's allowing us to do is return to something that feels like normal and then allows us to interact with people again. And so we saw that with Rapid and AMUG recently. And so I know that having those in-person interactions are incredibly important for building the relationships between not only internal to the organization, so I have to travel to Albuquerque next week to go to the mothership, but having the opportunity to be able to interface with people again is incredibly valuable and important to being able to do good work and find the right people to do the work with. So I've made a lot of connections at Rapid, what was it, last month or recently? But having that is something that I'm most looking forward to. It's less to do with the technical. I really think that there's a lot on the table that we can accomplish that's not technically limited. It has a lot to do with just being able to work with the right people on the problems at hand. That's true internally and that's true externally. I think that that's usually where we struggle the most, is just having those personal relationships built and then maintained to do good work.
Right on. So Tyler, thank you so much for joining the show today. Awesome stuff with all the work that you're doing, and looking forward to seeing you around the industry.
Thank you, Mike. Appreciate it.